Today, we're going to discuss isentropic potential vorticity, or PV. This content can also be found in Chapter 9 of Martin. To begin, we're going to begin with the vorticity equation in isentropic coordinates. To recall, isentropic coordinates are when we are on a theta surface. And so we're going to begin by writing the vorticity equation in isentropic coordinates. So d dt of the quantity zeta sub theta plus f equals minus the quantity zeta theta plus f times the divergence of the wind del dot v theta. Here, with this vorticity equation, we are signifying that we are in isentropic coordinates by the fact that we are on these theta surfaces, meaning we're on, for example, the 300K surface. Let's hold this aside for a second and then consider what does it mean if the flow is convergent. Here we basically have divergence, or convergence by a minus sign, in del dot v theta. We want to consider what this means for mass considerations. And so we know that if the flow is convergent in an isentropic setting, we know that the mass must increase. So how can we write this mathematically? Well, we need to go back to thermodynamics for some help and say that the mass of our air column, m, is directly related to the depth of the column by minus the change in pressure over gravity, g. And here, this delta p is a measure of the pressure interval between, say, our theta and our theta plus delta theta surface. So, for example, if we were thinking about our two isentropic levels here, theta and theta plus delta theta, we have a change in pressure here that is different in two different areas. This is delta P over here, and over here it's wider at a bigger delta P. We can actually bring this understanding into our understanding of continuity in isentropic coordinates via the following equation. Here we can say that our total time rate of change of the quantity minus 1 over g dp d theta, so basically a restatement here of the conservation of mass, is equal to minus 1 over g dp d theta times the divergence of our wind on our isentropic surface. Noting here that static stability sigma equals minus 1 over g dp d theta. So in essence, now we've got two equations. We've got our equation here relating to static stability in our mass continuity equation, and our vorticity equation in isentropic coordinates, both of which have this common del dot v theta that we can solve for. So let's go ahead and do so first with our vorticity equation, such that we can say 1 over the quantity zeta theta plus f times d dt of zeta theta plus f equals minus del dot v theta. Similarly, we can do the same for our mass continuity equation. And we can say, substituting in here for sigma, 1 over sigma d dt of sigma equals minus del dot v theta. Now that we have our two equations with the same thing on the right-hand side, we can put these two equal to each other, such that now we can write 1 over zeta theta plus f ddt of zeta theta plus f is equal to 1 over sigma d sigma dt. It turns out here we've got a very nice format for our equation, in that our ddt's cancel on both sides, and we are left with d zeta theta plus f over zeta theta plus f as equal to d sigma over sigma. This lends itself nicely to integrating both sides to then start to solve our equation. So let's go ahead and integrate both sides. We're going to integrate from zeta theta plus f naught to zeta theta plus f of our d zeta theta plus f over the quantity zeta theta plus f. And on the other side, integrating from sigma naught to sigma d sigma over sigma. Now, what you may notice or may realize is that this is basically our integrating of dx over x, which is actually a known solution. It turns out here that we're going to get a natural log out of this, such that then we're going to have the natural log of the quantity zeta theta plus f over zeta theta plus f naught equal to the natural log of sigma over sigma naught. Well, how do we go ahead and get rid of the sigmas on either side? That's correct. We're going to use the exponential. And so we can then go ahead and raise each side to the e. We're just going to get rid of our natural log, which will allow us to come back and say zeta theta plus f over zeta theta plus f naught equals sigma over sigma naught. Now the question is, well, what does the sigma really mean? Or what does the naught really mean, excuse me. Our naught here is just meaning it's a constant value, it's a starting value. And so we can isolate all those values together, and then all the non-constant values together, such that we have zeta theta plus f over sigma equals zeta theta plus f naught over sigma naught, which with our two naughts together we know just equals a constant, or we could just say equals c. So it turns out that for adiabatic frictionless flow, our ratio of absolute vorticity on our isentropic surface divided by our static stability is a constant. And so what we can say then is for adiabatic frictionless flow, PV, substituting back in here for static stability, sigma, equals minus g times the quantity zeta theta plus f times d theta dp. And this will be constant, meaning that it does not change provided that we remain adiabatic and frictionless. This would be a conserved quantity. And so PV gets its name from the fact that there is the potential for creating relative vorticity by changing the latitude. And we do so by manipulating our Coriolis parameter f. Or we could change PV by adiabatically changing the separation between our isentropic layers d theta dp. But we can't do one without changing the other to maintain our constant value of PV in our adiabatic frictionless setup. So the last bit we're going to do today is, so what is a common value of PV? We can go ahead and scale this equation. In order to scale this equation, we need to consider all the parts of our equation. And so let's think for a second about our relative vorticity, zeta theta, and our Coriolis portion, F. Remember, relative vorticity is on the order of 10 to the minus fifth per second, whereas our Coriolis parameter, especially here in the mid-latitudes, is 10 to the minus fourth per second. And so the one that's going to be more important here is our Coriolis. So what we're going to do is we're going to scale PV. I'm going to change colors here for a second, such that the scale of PV is going to be based on the equation minus G times F times our change in theta over our change in pressure. And so our scale for G then is 10 meters per second squared. F is 10 to the minus fourth per second. And our change in theta over change in pressure is going to be minus 10K over 10 kilopascals. And again, we'd want to convert our kilopascals to pascals to get all of our units to work out, or it'd be just 10,000 pascals. When we work out all of this math, what we find is that our PV scales to the following quantity: 10 to the minus sixth meters squared per second, K per kilogram. That's a nasty set of units. And so what we do is we define this as a new unit. We define this as 1 PVU, or 1 potential vorticity unit. Doing so allows us to determine what types of PV values are common in different parts of the atmosphere. And so in general, what we find if we have values less than 1.6 PVU, that means we're in the troposphere. If we are around 1.6 PVU, that would be the tropopause. And if we are greater than 1.6 PVU, this is stratospheric air. Commonly what happens, though, is that instead of using 1.6 PVU, we end up saying 2 PVU is what we call the dynamic tropopause, or DT. This puts us slightly on that stratospheric side, but that is what is generally used. And if you go out and find any sort of PV maps out on the web, likely what you're going to be looking at are 2 PVU surfaces instead of the 1.6. It's good enough for government work. And so that concludes this introduction and derivation of potential vorticity within our dynamic framework.